Hello everyone and welcome to PC Retro Tech. In this week's video we're going to be getting back to CGA graphics programming on my 8088 XT clone machine. This is early 80s technology, and if you've been following the channel you know that I've been writing a CGA graphics library in assembly language and also some CGA demo effects. But one that I've wanted to have for quite a while is to rotate a 3D object on the screen. Now, we tried this previously, but unfortunately there was a lot of flicker. If you know anything about animation, you know that you have to blank the previous image before you display the next one. And unfortunately the monitor and the CGA card in this run at 60 Hz, but the memory in the CGA card and of course the processor in the machine are too slow to update the entire screen at that frame rate. So unless you're very careful you get a lot of flicker, and this is in fact what we had before when I drew just a wireframe tetrahedron on the screen. But in this week's video what I'm going to do is draw not only a tetrahedron, but it's actually going to have filled sides, and I'm going to do it all without any flicker. So let's have a look at what it looked like before when we just had a wireframe image that was just drawing directly to the screen and flickering a lot. Admittedly, part of the reason for the flashing here is actually my camera, not the demo itself. But this is what it looked like when we tried to draw a wireframe tetrahedron rotating. To save computation, I actually had a little window around it so that it would keep the amount of data as small as possible. But of course, this is still always going to run slow because computing lines is computationally very intensive. Now, we have sped up line drawing just a little bit since I did this, but not very much. So the question remains, can we really draw a tetrahedron with a high frame rate on CGA with filled sides? At the time I didn't think so, but I now believe it's possible. So let's get stuck in. Well, if we're going to be drawing a tetrahedron on the screen, there's a few things we're going to need. The first is X, Y, and Z coordinates for a regular tetrahedron. And how good is Wikipedia? On their tetrahedron page they have a section on coordinates for a tetrahedron. Now, there's a couple of different versions given there, but the one I'm going to be using is this one here. Now, there are actually 4 coordinates there for the 4 points at the corners of the tetrahedron. There's plus and minus 1 in each case here, so that makes a total of 4. And the reason I want to choose these coordinates is that there's some zeros in there and also some ones. And multiplication by 0 and 1 is actually trivial. Of course, the other part of the coordinates is a real number, and we have to be a little bit careful about that because it means that we're going to be dealing with fractional values, and so some kind of floating point or fixed point arithmetic. And as you'll see a bit later, this is actually really slow if you just do it naively. But anyway, that gives us a set of coordinates. The other thing that we're going to need is a way of rotating these coordinates, and Wikipedia to the rescue again. On their rotation matrix page, under the 3 dimensions section, they have matrices for rotating a point about the X, Y, and Z axes by given angles theta. Of course, those angles can be different. You can rotate by one angle around the X axis and a different one around Y, and so on. Now, you shouldn't be afraid of matrices. There are even worked examples on this Wikipedia page. All we're going to need to do today is multiply this matrix by the vector, which will just be the X, Y, and Z coordinates of the point that we want to rotate. We're going to do that for each of the points in the tetrahedron, and that'll allow us to transform the tetrahedron in space and to rotate it around. Now, I'm going to make things a little bit more interesting by multiplying by 2 of these matrices with different angles theta, so that I end up with rotation about 2 of the axes at the same time. And of course I've done a little bit of algebra to simplify the result so that I can get as few operations as possible. But other than that, it's very straightforward stuff and pretty much anyone can do it. The difficulty with this is actually going to be the performance. So obviously we're going to need floating point numbers to represent sine and cos, and we'll need a floating point library. Fortunately, Ball and C has a floating point library, but it is very, very slow without a math coprocessor. We're just going to put up with that. I'm actually going to do all of this computation as pre-computation because it will be too slow to do it at runtime. And later on we can speed that up significantly by writing a customized library for doing rotations. Now let me show you what the result looks like when you actually apply these transformations to the 4 points of the tetrahedron. This is my code for computing the rotated coordinates of the tetrahedron, and the first thing it does is compute a sine or cos table, and you don't want to be computing sine and cosine at runtime, so doing a lookup is definitely the right way to go here. And then it does the rotations of each of the 4 points 384 times. And I just picked that number because it gives a nice fine gradation between each rotation of the tetrahedron. You can see on each line here there are 4 coordinates, and those are the 4 corner points of the tetrahedron, and they're just changing slightly. So there's x, y and z coordinates for each one, and as the tetrahedron moves about in space, the coordinates change very, very slightly. Now this takes 17 seconds, so only about 20 rotation matrices per second, which is incredibly slow. You probably have to use a fixed point library and something custom written at that in order to get this to run fast. But we'll just do it as pre-computation, as I said. So the thing that remains now is to take these coordinates and draw a tetrahedron on the screen. But these are x, y and z coordinates. How do we get x, y coordinates? Well, I remembered that if you want to do a 3D star field, you need to project from 3D coordinates into 2D coordinates. And this nice website by somebody by the name of Joe does just that. And he gives the perspective transform here, which takes x, y and z coordinates, multiplies by some focal length, and you end up with x and y coordinates. And he even gives some sample code in JavaScript, I think, but we won't be needing that. Let's run this transform on our 3D coordinates, and you have to do a little bit of fiddling, moving things about. What I want is values between -64 and 64, because that's roughly how big I want my tetrahedron to look on the screen. Let's see what the result is. This is the same program, but this time instead of showing you the rotated coordinates, I'm going to show you the perspective transformed coordinates. So now there are still 4 coordinates for each tetrahedron, but they're just x, y coordinates. And you can see that there are negative and positive values here. This is perfectly standard, but of course to get it onto the screen we're going to need to shift in the x and y direction so that we're in the middle of the screen. But other than that, that's all there is to it. We now have the coordinates for rotation of a tetrahedron. There's one final piece of maths that we need, and that is to figure out which faces to actually draw. You don't want to draw the ones on the back of the tetrahedron because they're facing away from you. So the way you do that is you look at a face front on and you give it a numbering 1, 2, 3, say clockwise, and if you flip the face over, the numbering will be in the reverse order, anti-clockwise. So how do you tell whether or not you have a clockwise or anti-clockwise orientation? Well, you can take points 1 and 2, which define a line, and try and work out, is point 3 on the right of that line or on the left of that line? If it's on the right, it's clockwise, and if it's on the left, it's anti-clockwise. So I literally typed into Google how to tell which side of a line a point is on, and up came a Stack Exchange question with lots of answers that are all equivalent, and they just say to use this gadget called the cross product. So you plug the coordinates of the points in, and if the value is less than 0, it's clockwise. If it's greater than 0, then it's anti-clockwise. And if it's 0, it means all the 3 points are on the same line. So obviously that would be a case you want to exclude as well. So you just go through all of the perspective transformed triangles, plug the coordinates into this formula, and then you can tell which faces you should draw. Now the next thing we're going to need is triangle fill routines, and unfortunately this is not a beginner project. It took me quite a few weeks to do this, but what you're seeing is the test code for this, and it's drawing 2 triangles sharing a common edge, and actually the base of the triangles is moving across like this. Now there's quite a few things to get right here. For example, if you have very narrow triangles of 0 or even 1 pixel wide, you have to figure out how to deal with that. And you also have to think about what to do on the join. If you have triangles of different colors here, which color do you paint the join? So it's not an easy project. The other thing I've done here is I've allowed non-solid fills. So in fact you supply 2 pixel colors and it alternates between them, and on the odd lines it shifts by 1 pixel so that you end up with a kind of checkerboard effect in the fill color. And this gives you 16 different options instead of the usual 4 colors, which just looks a little bit nicer. Now how does this work? Well, basically it computes the 2 lines first. In fact, it computes the X increments that are required for each drop in Y position. And so what this effectively gives you is the N coordinates for each of the horizontal lines that makes up the triangle. And so then you can just use a very fast routine, it's one of the fastest things you can do with CGA, to just draw the horizontal lines in between the endpoints. So this is actually only running at 4.77 megahertz, so it's actually quite fast, and it's certainly fast enough for our tetrahedron. So all that remains really is just to start drawing our tetrahedron using the rotated points that we have. Now this is what it looks like if you just draw the triangles using the fill routine directly to the screen, given the coordinates that we have computed. Now of course you can see that I'm not clearing the image between each new tetrahedron that I draw here, so you get a whole lot of mess around the edges. But I wanted to show you this because of the frame rate. So the frame rate here is about 64 frames per second at 10 megahertz, which is really good. It shows that the triangle draw routine's doing quite well. For whatever reason, I decided to have 2 different versions of the triangle draw. One which starts at a pointy end of a triangle, and another one which starts at a flat and goes down to a point. It turned out not to be necessary because by the time I got all the bugs out of my code, the 2 versions ended up looking identical. You can actually see there's even a join between the 2. There's a kind of artifact running across the middle here. You'll see that that disappears in a later version of this code. But I just wanted to show you this first attempt that I had at drawing a tetrahedron. Now, in order to get rid of the background here, you could just draw into an off-screen buffer and then blank the buffer between each frame and copy the buffer over to the video RAM only after you've redrawn the next tetrahedron. But that's going to halve the frame rate, so we'll end up going from say 65 down to somewhere in the 30s probably. I decided to try a different technique, which is to actually just draw black across to some fixed point either side of the image. Now you have to be careful about that because you can't draw black from the edge of every triangle, otherwise you might black out part of another triangle that's needed. So you have to compute which edges are actually really on the edge of the tetrahedron. And in order to do that, I just make a list of all of the edges that are shared between triangles and mark the ones that are displayed on the screen because both of the triangles are displayed, and those ones have to be inside. All the edges that remain must be on the outside, and so I can just draw across to the edge to clear to black. Now the other thing you have to do is worry about the top and the bottom. You can see that just drawing edge to the edge of the screen won't be enough. It can be that the tetrahedron moves up or down as it rotates and leaves behind some stuff at the top and bottom. So you also have to clear some lines above and below the tetrahedron. But let me show you what it looks like with the clearing to black finally implemented, and we should then have a tetrahedron rotating. The other thing is that here I picked a rotation rate in one direction. It's exactly 3 times the rotation in the other direction around the other axis, and it just so happens that you only ever see 2 sides of the tetrahedron if you do this. So in the next version you'll see there will be cases where you'll actually see 3 sides at once. And here it is at last, folks, a 3D tetrahedron with filled sides rotating at 35 frames per second on a 10 megahertz 8088. Now of course that's come down quite a lot from the 65 frames per second that we had when we weren't clearing to black around the edges. So I tried a few other things. For example, you can actually have it, instead of clearing all the way to a fixed point, have just a small amount of black around the edges. Now the problem with this is that if a horizontal line shifts, it can actually be a lot of black that you need in the horizontal direction to clear it. And so what I did is I came up with an adaptive clear So the amount that you clear along in the horizontal direction depends on the slope of the line. But unfortunately, the end result was exactly the same speed. So another way that you could speed this up, and I haven't tried this because it would be a lot of work, and frankly I don't know how, is to skip drawing the middle portion of the triangle, because if the triangle only moves a little bit, probably that doesn't need to be redrawn. But there's a couple of problems with this. First of all, figuring out when to stop and start again takes cycles, and it really doesn't take very many cycles to draw words of data across the screen. You're only looking at a few cycles per pixel. So the other problem, of course, is exactly the same as for the clearing. When you have a horizontal edge that moves, it's really not easy to determine exactly when you can safely skip drawing the middle of a horizontal line. And I don't really know an algorithm for this, so if you do know one, by all means drop it in the description below. Now the other way that we could speed this up, of course, is to not use graphics mode and use larger pixels in text mode. But I kind of like the appearance of this. It's nice and fine and definitely appeals to the eye, or at least to my eye. But it is a little bit slow now, don't you think? Once we've done the clearing to black, the frame rates dropped down, and it meant the whole thing looks slower. But we can get around that to some extent by actually just rotating by a larger amount between each frame, and that'll make it look like it's running faster. So let's do that now and see what happens. Well, here it is with a rotation speed of 5 around one axis and 6 around another axis, and of course you are getting all three visible sides at once in some cases. So this looks a lot faster, even though the frame rate is exactly the same at 35. But now that you have the higher rotation speed, there are artifacts at the corners of the tetrahedron. And that's because the triangles are rotating by so much that there's a gap between the old triangle and the new triangle, and of course you're not wiping that away quick enough for the eye to not notice the gap. So the only way you could fix that would be to get the frame rate up higher so that everything can be drawn before the electron beam gets around again, so you never see an inconsistent image. And as I mentioned, you could use text mode for that, but I'm not going to do that here. The other way, of course, is to draw to an off-screen buffer, as I mentioned. And then once you put the image back on the screen, you've only got consistent image data going back onto the screen. Of course, you still have to worry about the electron beam getting around in time, otherwise you'll end up with tearing, but that can be done with a little bit of fiddling. So what does the future hold for this? Well, obviously it'd be nice to rotate some other shapes like a cube and an icosahedron and various other things. And the code that I've got is more or less general enough to work with any convex shape. Of course, if you have something that's not convex, then all bets are off. That's actually a very hard problem to solve. But the code needs a lot of cleaning up first. So what I'd like is an interface where you specify a set of points, a set of lines between the points, and a set of faces involving those lines, and then have the code work everything out for you. So at some point I will write all of that up and put it into the graphics library repository, which you can access at the link in the description. But for the time being, it just draws a tetrahedron and rotates it. As you can imagine, it's difficult to keep up with a filming schedule on a YouTube channel. Sometimes things take a long time to debug. In fact, when I wrote this code, it took an enormous amount of time to get all of the bugs out of the clearing to black routines. There are so many corner cases and special cases, and of course a lot of different things that I tried to get the speed up. So unfortunately, this is what we have for now. But I'm pretty happy with this. It's something that I really wanted to do for absolutely ages, is 3D rotation on CGA in graphics mode. So I'm very happy to be finally there at that point. If you also enjoyed this, don't forget to give a like on the video and think about subscribing if you're not already. That's really all that I have time for this week, but of course there'll be plenty more CGA madness to come, so hopefully we'll see you in a later video. Bye!